Okay, so what we're going to do now is wrap up a reviewing. This is the last part of chapter 4, and it is about integration by substitution. Okay, when this is done, then we can start the new material, which is chapter 7. So this is actually a good topic to cover now because chapter 7 is all about applications of integration. So now this one, of course, you've seen before, but I just want to point out that it is a direct consequence of the chain rule that this approach works. So we're going to go back and quickly revisit the chain rule, and then we'll see how that applies here. So first things first, if you remember the way the chain rule works, is what we're trying to do is find the derivative of what's called a composite function. Okay, so it looks like this. And by the way, there's more than one way of writing it, of course. That happens so often in calculus. So if you write it as f of x and g of x, the derivative of this expression is f prime of g of x times g prime of x. Oops. Okay, so and of course the primes indicate a derivative. And so the first thing I want to do, though, is quickly review what composite functions are all about. So if you see something like this, it means that f is a function of g, which is in turn a function of x. So you also could define equivalently something like this. And again, they're both composite functions because it's a function of a function. And sometimes this one is written as f of g, or actually FOG, or FOG without the x. Here we can write this as GOF of x or GOF. How do we actually do this, though? How do we create a composite function? Well, let's look at a quick example. Let's say that f of x is 2x squared plus 2, and g of x is, let's say, 3x. Okay, so how would you combine these and come up with f of g of x? Well, the idea here is that wherever you see an x in f of x, you replace it with g of x. And of course, then you solve for it. Now, like here, you've got 3x squared, and then that becomes 2 times 9x squared. And then we ultimately end up with 18x squared plus 2. And then if we wanted to know g of f of x, so actually, let me quickly copy these down so we can see it better. F of x is 2x squared plus 2, and g of x is 3x. All right, so here's what's going to happen. Um, Everywhere in g of x you see an x, we'll replace it with f of x. So this becomes 3 times f of x. And now we substitute 2x squared plus 2, and we multiply it out. And this is our composite function, g of f of x. All right, now the next thing we're going to review is the chain rule. Okay, now the chain rule, as I just mentioned, is designed to let us calculate the derivatives of these composite functions. So how does it work? Um, oh, I just realized I left out a prime here. So this is our chain rule, and let me just copy it down here. Okay, let's bring that down here. Okay, so why don't we do this? Why don't we apply it to these two functions? All right. And also, as of course we just discovered, f of g of x is 18x squared plus 2. And in order to do this, we'll also need to know g prime of x, but that's easy. It's just 3. All right, so here we go. So we're taking the derivative of 18x squared plus 2. And now we could do this just using the rules that we know, but why don't we go ahead and use the chain rule anyway? Now f prime of x, looks like I forgot to write that one down. F of x is 2x squared plus 2, as you can see up here. F prime of x is 4x. So what we're going to have here is 4 times g of x, because we're going to replace all the x's in f prime of x with g of x. And then we'll make the substitutions. And again, g of x was 3x, and g prime of x was 3. And if you multiply that out, you'll get 36x. Okay, so now in a case like this, these functions were much too simple to really require the chain rule, but it's good practice. Okay, so anyway, what does this have to do with integration? Well, it turns out that integration, at least the technique we're about to use, is inversely related to the chain rule. Okay, so how does that work? All right, let's see. So if you start out by noting that the chain rule tells us that d dx f of g of x is equal to f prime of g of x, g prime of x. It turns out that the chain rule also implies that the following is also true. And just as a quick reminder, capital F of x is the integral of f of x. And if I differentiate it, let me write it like this. D dx, it just brings us right back to the original function. Okay, so that being the case, f prime of x, capital F that is the same thing as the original function. Because what this notation means is that you're integrating and then differentiating the same function. And that brings us back to the original function. And in fact, we may as well add this very important result right here. Um, Integration, actually, I should say indefinite integration, which means we're not looking for a specific constant. And differentiation are inverses of each other. All right. So that being the case, we can make the following claim. Let's copy this result one more time. Let's see. There it is. This is what I want right here. All right, I'll copy it. Sometimes it lets me copy, sometimes it doesn't. F of g of x, sorry. Okay, so if I integrate this side, what do I get? All right, well, it turns out, of course, that since these are equal to each other, it must be true that f prime of g of x is equal to f of g of x. And so therefore, what we actually have here is the same thing as um, f of g of x, g prime of x, dx. Okay, so in other words, if we're taking an integral in this form, this is the result. So now integration by substitution, when you apply integration by substitution, this is what you're actually doing. Now, the one thing I do want to point out, though, is that the notation here is in terms of f of x and g of x. You may have seen this done in terms of u's and du's and dx's. And so you can write this slightly differently. If you let u be g of x, then du dx is, of course, g prime of x. And in turn, du equals g prime of x dx. All right. So if that happens, then this is equal to f of u, and g prime of x dx is du. So if you notice, let me just copy this one more time. Since we just showed up here that this is equal to capital F of g of x plus c, once I replace all these terms with the equivalent functions of u, I've got very simply, oh yeah. And so you may have heard of this referred to as u substitution. So I personally find this to be much simpler to use than the G's and the F's. They just get confusing to me. There's just one way in which this is disadvantageous, which we'll get to in a bit. But just as far as it making sense, I think really this is the way to go. Okay. So we're going to get some practice here, making sure we understand how this works. So we'll start with, let's say, this easy case. So now remember, what are we trying to do here? All right, well, if we're going to use the F's and G's, um, yeah, this is what we're after right here. Okay, so in other words, this is your g of x, but f of x, which is, by the way, this is sometimes called the inner function when you have a composite function. And then f of x is the outer function, which would be the x squared here. Now, let's just say that we decide to make this substitution. Then g prime is du dx. Actually, no, we're not using u just yet. Sorry. G of x, g prime of x is 2x. We'll get to the u's in a minute. And so f of x is x squared. So f of g of x is going to be g of x squared, which in turn becomes x squared plus 1 squared. So that means that our integral is x squared plus 1 squared. Then we have g prime, which is 2x. And then we also have a dx. Okay, but we just got through showing that this is equal to the integral, or capital F, of x, of g of x plus c. Plus c because this is an indefinite integral. All right, well, that's one thing we haven't done yet. So if f of x, the original function, is x squared, capital F of x is the integral, which in turn is x cubed over 3 plus c, which therefore means now remember, g of x was 2x. No, sorry, x squared plus 1. And that's your final answer. Yes. Okay. Now, it's uh, it's kind of convoluted there. Yeah, I mean, but if you wanted to do something a little different, like using u's and du's, you could have just as easily done that. The u takes the place of g of x, and that is x squared plus 1. And of course, that means that du dx is 2x, or du is 2x dx. Now, we also have to recognize that y in these cases is a function of u. And then um, in this case, that would be u squared. Okay. So this original integral from way back here, let's copy that down here, could be rewritten as um, given that, remember, let's not forget, u squared and u is x squared plus 1, and du is 2x dx. So we ultimately end up with x squared plus 1 squared can be rewritten as Well, that's not so hard. And then, of course, we know that it's u cubed over 3. And now the u, because u is set equal to x squared plus 1, and you can see it's got to be the same answer. All right, x squared plus 1 cubed over 3 plus 3, plus c. Okay. So, you can take your pick. I don't think that when you do WebAssign problems that they'll insist that you follow one approach or the other. Okay, so I think we have a couple more examples here. Yes, we do. How about this one? All right. Now, what we should probably do is first rewrite it slightly. All right. So I'm going to assume that you feel the way I do, that you're more comfortable with U substitution. So if we all agree on that, then let U equal x squared plus 1. That means y is u to the fourth. Now here we have du dx is 2x, which means that du is 2x dx. So, oh my God, what happened? So this expression is equal to u to the fourth, and du is, of course, 2x dx, as you can see over here. And now it's easy because we're just applying the power rule that we know for integration, which is, hold on one second. And of course, don't forget the constant. All right, so that means what we have here is u to the fifth over 5 plus c. And now I can replace u with the original definition, which is x squared plus 1. All right. And that's how it works. Hmm. Let's see, what else do we have here? Oh, here's a good one. All right, so I'm going to rewrite it again slightly. And then I'm also going to do this. Okay, so let's do this. Let's have u be x cubed plus 1. Then y would be u to the 1/2 power. Du dx is 3x squared. So therefore du is 3x squared dx. Okay, great. Now, by the way, if it doesn't work out, let's say we don't have exactly what we need to proceed, sometimes we can supply missing constants. But if that's not the real problem, if there's some other holdup, then we have to try something different. Okay, so here, for example, we have, and that's going to be u to the 3 halves over 3 halves plus c, which is the same thing as 2/3 u to the 3 halves plus c. And of course, u originally was defined as x cubed plus 1. And that's our answer. And if you're not sure, you can differentiate it and prove that it is in fact correct. All right. Um, Now, of course, we can't get away without having some trig integrals. But before we do that, I would like to remind you that, ooh, if f of x is the tangent of x, f prime of x is the secant squared of x, just in case you forgot. Okay. It's like there's so many trig results. We can't possibly memorize them all, but just as to refresh your memory. So the actual question is this. All right, so here's what we're going to do. Now, by the way, if you start to define u and you find yourself with results that don't make any sense, you can just try something different. You're not stuck. So here, what I'm going to try to do is let u be tangent x, and then y would be u plus 3. If that is not correct, if that's not the way to go, we'll find out pretty quickly because we're making a bigger mess. So then du is secant squared x, and therefore du dx, and then du is secant squared x dx. So you're in trouble. Whenever you're making things messier, you're doing something wrong in calculus. So that would leave, now, by the way, let me rewrite this. I just prefer to have all the parts together. So in other words, it looks nicer if this is just du. And then here we have the integral. And so what do we end up with? And so u is tan x. And that's it. We're done. Okay. All right. So now what else can we do? I'm sure I have some more examples here. Um, yes. X squared plus 1 to the 4th dx. Or we can write it like this. Now, this is an interesting case. You'll see why in a minute. Let's try u equals x squared plus 1. And so du equals 2x dx. All right. But the original function is this. And then I'll rewrite it slightly. And you'll notice we don't actually have the du that we need. We have u to the fourth, that's fine. But we don't have du, but we're awfully close. In fact, we're only missing a constant. If only there was a 2 here, we'd be all set. But that's not a problem because here's what I can do. Oh, can I multiply and divide by the same number? Of course. So therefore, by doing it like this, I have u to the fourth, and this is my du. Well, now we're all set. And we make our substitution. U was defined as x squared plus 1. And of course, I can multiply the 1/2 by the fifth there, and that becomes 1/10. And that's it. So in other words, this one wasn't exactly set up perfectly, but we were able to substitute in a constant and turn it into the form that we really needed. Now, if we were missing an x or something like that, that's different. We can't just plug it in, but with a constant, we can. And so we always want to keep our eyes open for cases where it's almost there. It's just missing a constant. So we can provide it as long as we are consistent. In other words, don't multiply and then forget to divide. Otherwise, you're changing the answers. All right. Now, all of these examples were based on indefinite integration. Okay, so what about definite integration? Does anything change? All right, so in other words, so indefinite looks like this, whereas definite looks like this. We have an upper and a lower limit of integration, which means we're trying to solve for a specific constant. Whereas up here we have a family of solutions. Here we have one solution, which is a constant. And by the fundamental theorem of calculus, what we're actually doing is evaluating the integral at b and a and subtracting. Well, what we have to watch out for here is this. When we use u substitution, we must adjust the lower and upper limits of integration. Okay, because they won't be the same, or not likely, because those limits refer to f of x, and we're dealing with u of x. Okay, so something has to be changed. So they have the specific formula right here somewhere. Let me go find it. Oh, okay. Well, all right. Well, maybe we should have done this one first. Nah, these are the same ones, exactly the same we were doing. We don't need to do every single one of them, but they do want you to know that this is the result of what's called the general power rule for integration. So no matter which one you use, You know what? I'll tell it. Let me do this. Let me sneak this in here. And that's just exactly what we were just doing a few minutes ago. Just remember here, u is g of x. Okay, now we can get back to this. I guess we don't need this. All right, so indefinite integration looks like this. And definite integration looks like this. So there it is. Okay, this is the result we're looking for. So you notice what's happening here. This is here we're integrating the chain rule again, and we're solving it as f of u. So remember, in this case, u is g of x. And then we also will need um, so what they're noticing, showing you here is that um, the a is replaced with g of a, and the b is replaced with g of b. All right, so I have an example of this right here. Let me just get it out. Ah, here we go. So here's the setup. We need to integrate from 0 to 1, x, x squared plus 1 cubed dx. So we know how to do the indefinite integral part. So let's take care of that first. And let's just say u is x squared plus 1. Y is u cubed. Du dx is 2x. Du dx, oh, sorry, du, just plain du, is 2x dx. Now, if you notice, like in an earlier example, we don't actually have that, do we? So we're going to rewrite this slightly. And now this is my du, and this is u cubed. But now here's the thing, though. We have to change these limits of integration. So how do we do that? Well, u of x is defined as x squared plus 1. U of 0 is 1, and u of 1 is 2. So that means that the bottom one can stay the same, but the upper limit has to go to 2 now. Otherwise, we're going to end up with different results. Oh, sorry. What am I saying? No, it's they both changed. It's from one to 2. Sorry. Now we're all set. Okay, we can do it now. So this is the book. Most books use this notation. This is meant to indicate that you're evaluating it when u equals 2, and then you're going to do the same thing with 1 and then subtract. Okay. So 2 to the fourth is 16. So it's 15/8 and no constant. Okay. All right. Now, at this part of the chapter, they're going to show us a couple of interesting things. Um, special rules for special circumstances. And for example, you may recall the concept of odd and even functions. All right, let's just quickly review that. Okay, now first things first, not all functions are either odd or even. In fact, many of them are not. But in a case like this is the case where the function is even. All right, now the classic example of this is x squared. Why is that? Because no matter what values I pick, let's say well, all right, let's do 3. And no matter what numbers I pick, the same thing will happen. They'll both be the same. And you can tell from the graph if the curve is symmetrical with respect to the horizontal axis, that's how you can tell that it's an even function, meaning the left and the right are mirror images of each other. Now, an odd function, on the other hand, looks like this. And that means that f of x is an odd function. And the classic example of this is x cubed. So let me just give you a quick example. So if you notice, they're the negatives of each other. For every, no matter what x is, we'll have the same thing. So here, when you graph it, you'll find out that let's say 2 and 8 is here, which implies that -2, -8 has to be down here. And so here we say that the function is symmetrical, not with respect to the vertical axis or the horizontal, with respect to the origin. And the way to think about that is that the first and the third quadrants are mirror images of each other. Okay. That's what it means to be symmetrical with respect to the origin. And it can also happen from the second to the fourth quadrant. Okay. So this is what even and odd mean. Now, what does this have to do with anything? Well, as far as integration is concerned, you can see with an even function on the left, we can calculate the area under a curve by taking the integral over that entire interval. But with an odd function, we have a problem. Look at this. We have negative areas and positive areas. If I integrate directly, I'll end up with 0. Okay. And that's not what I want. So that's why this is important. So here's the results. If f is even, like we see here, we integrate between negative and positive a. It's equal to, well, we know that it's equal to, but I just want to mention that too, but we can also simply note that the area is the same on either side because of that symmetry I mentioned. So all we have to do is this. We can rewrite it as 2 times the area between 0 and a. All right. But for the odd function, well, guess what? The two sides exactly offset each other because this is positive, this is negative. They're both the same amount. And so you will, in fact, end up with 0. Because the negative and positive areas exactly offset each other. Okay. Let's see, what else do they have for us? Let's see. I think we're kind of done. There's a few more applications here, but since this is review, I think what we'll do is we'll stop it here, and then the next time we meet, we can finally start chapter 7. Okay, I'm sure you're dying to see what it is. In fact, I'll tell you what, let's open it up right now and see what it's all about. Applications of integration, specifically the region between two curves. And there's different ways of doing this, of course. And we're also going to do the same thing from left to right later on. Yeah, like that one. So you can see all of this is 100% based on integration. So it's a good thing we've refreshed our memories. Oh, that was it for one. Okay. And then part 2, 7.2. Now these are volumes. Volumes are very tricky. Um, areas are one thing, but volumes are a little bit different. So, this is every calculus book covers this area. I mean, it's something you want to be exposed to at least once, but this is very helpful for like finding the areas of volumes, let's say of cones and that kind of thing. And so we're going to integrate either from top to bottom or left to right. And it'll turn out both approaches will, of course, give us the same answer. Yeah, there's all kinds of techniques we can use here. And then the shell method, yes. And it's just another way. This is for more complicated cases. So, and then the last part, arc lengths. Okay. How can you tell how far you traveled along a curve? Now, all of this is fine as far as it goes, but in chapter 8, what we're going to see in 8 is some extremely complicated um, integration techniques. We've learned the basics so far, and that's great, but there's a lot more for us to go. There's a lot of different integrals you may encounter, and let's just say we're going to dive more deeply into integration. We're going to learn a lot more complicated rules so we can handle more advanced cases, and this is going to take quite a while. Integration is a very complicated topic, let's say, compared at least to differentiation. So this will take up quite a bit of our time. So anyway, but lots to look forward to. So in the meantime, I think we're good with our reviewing. I think we're caught up with what we needed to remember from Calc 1. And so, and this book, by the way, does have Calc 1 in it. It's not just a Calc 2 book. So if you want to go back and revisit, you can do it at any time. And so I'll see you all next time.